show one page at a time. I would like to continue. You see my screen?
That's better now.
Okay. So I'm going to scroll through my talk instead of showing one page at a time because of the problem that I have with this. Sorry, my apologies. So I'm going to continue with the idea of using stars to study fundamental physics, fundamental forces. I will use the closest star to us, the sun, and the furthest away star to us, type 1 supernova, to study some fundamental physics. So greeting from University of Connecticut. We are somewhere out there between New York and Boston in this beautiful coastline of Connecticut. I will start by studying a middle-aged star, what we call the sun, and with the standard solar model that allows us to study some fundamental interaction. We understand the sun in a very great detail in this time. We even have pictures which are, for example, this will be just a small section over here, which we observe today. Of course, the model that we have of the sun goes all the way to the core, to about 5% of the radius of the sun. And as we will see, the model seems to be working very nice. So the first thing that we know, the sun shines. The sun shines, that means that it emits energy on us. It has luminosity. The luminosity, as we understand, is deriving from burning hydrogen to making helium. Well, the sun, like all of us, must obey the laws of physics, must obey conservation law. On this side of the equation, we have 4 baryon. We also have 4 baryon over here. 4 proton, 2 proton, 2 neutron. Baryon number is conserved. Now we must conserve charge. So here charge 4 plus, 2 plus, we must emit 2 positive charges to positron. Well, since we created a positron, we now have to conserve lepton number, so we must emit neutrinos. The sun is inescapable. The sun, if it follows the laws of physics, must emit neutrinos. The sun conserves energy. If we take the mass of the hydrogen minus the mass of the helium minus the mass of the positron, multiplied by c squared, we get 25 MeV. The neutrinos, on the other hand, takes about 250 keV, so it immediately follows. The luminosity of the neutrino must be 2.3% of the luminosity of the sun. If we know how much energy comes from the sun, we know how much energy should come from neutrinos. Well, we know the luminosity of the sun very well, 1.3 kilowatts per meter square. Our life depends on this luminosity. We know this number very well. We know the distance from the Earth to the sun. So if we now take the local irradiance, local luminosity, and we go to 4 pi times r squared, r is astronomical unit, we get the luminosity of the sun. If, in fact, we know this number with 1%, then we know the solar neutrino flux with plus or minus 1% accuracy. There is no other source of neutrino that we understand so well. Even neutrino that come from a reactor, we don't know with this accuracy. The sun is the best source of neutrinos. If we want to study neutrinos, we have to look at the sun as we've been doing for the last 60 years. In more detail, here I just wrote to you in general, in more detail, what the sun first does is burn 2 hydrogen to make deuterium and neutrinos, which we call electroneutrinos or PP1, proton-proton 1 chain. The sun can also fuse helium-3 and helium-4 and make beryllium-7 neutrinos. That's from the beta decay of beryllium-7. Those are the PP2, proton-proton chain 2 neutrinos. And beryllium-7 can interact with hydrogen to make boron 8, and that create, again, neutrinos three types of neutrinos. John Bacall, in his book, Neutrino Astrophysics, has in fact calculated the last 60 years, well, he's not alive today, but ever since he was alive, he was calculating. And this is the spectrum of the neutrinos that we observe. This is the spectrum as a fraction of the radius of the sun. So you can see most of the energy, most of the neutrino, most of the reaction occur within 30% of the radius of the sun. The boronate neutrino comes from about 5% or 4%. So if we now measure the boronate neutrinos, we measure what's happening in the center of the sun. We are able to probe the center of the sun. In the year 2000, it was clear that we now have a standard solar model, but we had a problem. The arrow bar on the neutrino fluxes, this will be the boronate, this will be the beryllium-7, and this will be the PP1. The arrow bar was too large. 20% is not a reasonable error. It was clear that we need to clean up the nuclear physics of the sun. It was clear that we nuclear physicists had to do something to get better accuracy on the standard solar model. The standard solar model simply take input from laboratory measurement and create the standard solar model spectrum. At this point, I came up with an interesting idea. Originally, we thought it will never work. In the sun, we fuse beryllium-7 and proton to make boronate plus a photon. The idea is to make photon interact with boronate to look on the time reverse process. Physics allows us to do that. Where do we get the photon? The photon are in fact virtual photons. They come from a process which is very well understood in physics, a Primakov process. For example, when a real photon interacts with a virtual photon from a high Z nucleus through the Coulomb interaction, it can create a pi 0, and then the pi 0 can decay to 2 photons. In 1951, Primakov proposed this process, and that's how we know the lifetime of the pi 0. So the idea that I had, let's have a beam of boronate passing by high Z nucleus and exchange a virtual photon and look on the proton and the beryllium-7 coming out. We have to be far away from the nucleus, so there will be no nuclear interaction, only Coulomb interaction. We have to be about 40 Fermis away. And if we do that, that means everything is in the forward angle. So in fact, we went to Japan, to Riken, where we produce a radioactive beam. We collide carbon with a target, produce a lot of material. We process this material with electromagnetic interaction, with a dipole magnet and electric field, and we can get a boronate beam. The boronate beam impinges on a lead-208 target, and we measure in the forward angle the proton and the beryllium-7 from the interaction. If we measure the form momentum of the beryllium-7 and the form momentum of the proton, namely, we measure the energy and the momentum or the angle of the particle, we can calculate the invariant mass. Invariant mass is invariant. It's independent on which system we're looking, in which coordinate system we're looking, and the invariant mass is what we're after. Here is the experiment at Riken, target over here. This is our hodoscope, and you can see even a few Americans over here, but all the rest are international students. I always like to note that the only person who has a jacket which is dirty is the graduate student. All of us look very clean and very ready to do the experiment. Vasa did this PhD and received some prize for this. So basically at this point, if the system works, it's really magnificent. And here I quote my friend Yigal Talmi, when a dog speaks, it doesn't matter what it says. The fact that we are able to do this reverse process, the reverse process over here, we're able to measure it with virtual photon, just like what Primakov proposed in 1951, is in itself quite an achievement. But maybe we can listen to the dog. And what happened is the following. The uncertainty, the large uncertainty in nuclear physics was caused by two data sets that disagree. These are the green one and the blue one, they disagree. And our experiment agreed with the lower values and not with the upper one. That led to a lot of discussion in the community. In 2011, some 40 physicists came together and says, we must clean up this mess. We did, and today we know all the nuclear input with high precision of the order of 3 to 5%. And we can now look on the standard solar model with high precision. Of course, all of this started already in 1964 by John Bacall and Ray Davis. In fact, I'm sure you know, Ray Davis got the Nobel Prize in 2002 for this measurement. What Ray Davis did, he had a tank full of cleaning agent. When you go to the dry cleaner, they don't clean your clothes with water. They clean it with carbon tetrachloride. That's a cleaning agent. 600 tons of this in this tank. And in this tank of 600 tons, every 3 days, one chlorine atom changed to argon, chlorine 37, changed to argon 37, which is radioactive. So we have every 3 days, one atom. In a month, we have 10 atoms produced in this huge tank. Ray Davis found a way to actually detect those atoms, and he has been doing it since 1964. Of course, no longer, Ray Davis has passed, but for that work, which is a remarkable achievement, he received the Nobel Prize in 2002. A new experiment came, and that's the Sudbury neutrino experiment. The Sudbury neutrino experiment does not use carbon tetrachloride. It uses heavy water, D2O, and look on dissociation of deuterium by the neutrinos. And here is the situation in 2004. The chlorine experiment saw about discrepancy of maybe a factor of 3.5 between the solar model and the observed value. And so did all the experiment except for snow. Snow, when looked in one way, similar to what chlorine did, reproduced the result of chlorine. So about 1/3 of the neutrino. Okay? But if it looked another way, it saw the full flux predicted by the standard solar model. So by looking on the dissociation of deuterium, we for the first time saw a clear evidence that the standard solar model is correct, because when we look on the dissociation of deuterium, we see the full flux predicted by the standard solar model. But when we look in a different way, what we call charge interaction, this will be a neutral current interaction, this will be a charge current interaction, we reproduce the result of the chlorine experiment. So in the Sudbury neutrino experiment, we can dissociate deuterium to 2 protons. We can dissociate the deuterium to proton plus neutron, or we can do elastic scattering with the atomic electron. This goes through charge current interaction, and this goes through neutral current interaction. When we measure the neutral current interaction, we measure interaction with all neutrino, tau neutrino, electron neutrino, and mu neutrino. When we measure charge interaction, we only measure electron neutrino. And this is basically the figure that allowed us to declare victory after 40, 50 years of work. The Sudbury Neutrino Observatory observed the full neutrino flux as predicted by the standard solar model. But here on Earth, it sees only electron neutrino 1/3. So clearly, on the way from the sun to the Earth, something happened to the neutrino. They oscillate from one type to the other. And that was a discovery that allowed us to conclude the neutrino have a mass. It is the first deviation from the standard model of particle physics. It was worthy of a Nobel Prize, and the man is clearly a wonderful man. Art McDonald shared the prize with Kajita. Kajita looked at atmospheric neutrinos. Art McDonald, who is the spokesperson and in fact the driving force behind SNO, he was not the originating of the idea. When the idea originated, he was still in Princeton, and he moved to SNO because he realized that he has here a lifetime opportunity to do very good fundamental physics. Today, we know the neutrino have a mass. It is one of the most important discoveries of the last century, that neutrino have a mass. The standard model has to be expanded, and the ramifications for this are incredible. This is how we use the closest star to us, the sun, to study fundamental interaction, fundamental properties of matter, the mass of neutrino. Now we move to the furthest star. They are as far away as the edge of the universe. Type 1a supernova. Type 1a supernova create light as an entire galaxy. So if we look at the end of the universe and we see a galaxy that all of a sudden is double its luminosity by a factor of 2, double is of course by a factor of 2, we know that a supernova exploded there. Supernova originally were classified by the absorption line. The light that comes to us have absorption line. So if we have no absorption line, we call it type 1 supernova. If we see absorption line, namely hydrogen is present, then it's type 2. Type 1a has no hydrogen line and has silicon 2 line. Type 1a supernova are the supernova that we would like to study. Here I'm showing you what a type 2 supernova would look like. Type 2 supernova is different than type 1a supernova, as you'll see in a moment. But in both those supernova, there is a fundamental problem in nuclear physics that we are still struggling with it today. The first measurement was in 1974. Today, we are still working on the problem, and that is known as oxygen burning. This is a problem that keeps me up at night for the last 15 years. Helium burning is the second stage after hydrogen burning. Hydrogen burning is what we saw happen in the sun. Helium burning has 2 stages. First one is 3 alpha particle make carbon 12, and that happens through a very special state we call the Hoyle state. Hoyle predicted this state in 1953, and it was discovered in 1954. In fact, we exist because this state exists in carbon 12. If that state did not exist in carbon 12, we will not exist. The production of carbon 12 in the universe goes through a resonance absorption of alpha on beryllium 8. First 2 alpha particles for a very short while create beryllium 8. A third alpha particle jump in and do resonance absorption on this state. If we didn't have this state, the rate of carbon, production of carbon, would be too small There won't be enough carbon to make all of us, and probably none of us will exist. It turns out at the same time that we make carbon, we also make oxygen. And this is the problem of current interest. What is the rate for making carbon plus alpha to O16? The fusion of carbon plus alpha to make O16. Since we don't know this rate, we don't know the ratio of carbon to oxygen at the end of helium burning. So, for example, I discussed type 2 supernova. Type 1a supernova come from a binary star. Is a Chairman telling me that I am running out of time?
There much you have a couple of minutes.
Okay, I will finish in a couple of minutes. So type 1a supernova is a dwarf, a binary system of a dwarf and a red giant. The dwarf steals hydrogen from the red giant. It starts as carbon to oxygen star. It grows larger and larger and then explodes. Here is an example of a type 1a supernova that was observed in 1972. Here is a supernova that was seen by Tycho Brahe, 1572. It was type 1a supernova. Later, 30 years later, the Korean observatories and Kepler saw a supernova. That's at the year 1604, 30 years after Tycho Brahe. And what we see over here is called a light curve. The supernova will become brighter and then decays. And you can see the scale is hundreds of days. Now, since we know that these supernova are 1.4 solar masses, we know how much light should be emitted by them. So we know how much light we detect. We can use it for detecting or measuring very large distances. So in fact, here are supernova at a very large distance, about 500 million light years away from us. This is the light curve, okay? And the light curve, as you can see, are almost the same, but about a factor of 3 different. Mr. Phillips in 1993, working in Chile, has discovered that if I now stretch this guy in this direction and in this direction by the same amount, by the same stretching factor, all these supernova lie on one beautiful calibration curve. So now I can use this calibration curve. I look at the supernova at the end of the universe, I put it on this stretching factor, I put it on this calibration curve, I know how much light was produced, I know how much light was observed, I can measure the distance. And here comes again, I'm sorry that I cannot show one slide at a time. The supernova in immediate vicinity within 500 million light years are all lie on a beautiful straight line. If you look very careful, maybe I can just do that. No, I cannot. I cannot do one. No, I cannot do. So when we look on the supernova in our immediate vicinity, they all lie on a beautiful straight line. Then we go to supernova at 5 billion light years away, and they're about 25% dimmer. So that means that sometime 5 billion light years, 5 billion years ago, something happened and the expansion of the universe accelerated. So those supernova are at 25% dimmer, which means they are further out from 5 billion years ago. That is what we call today the accelerated expansion. We believe that some mysterious dark energy causes this expansion. We have no idea what this expansion is, but it was good enough for the Nobel Prize for Perlmutter, Schmidt, and Rees. So today, this is what we believe is the composition of the universe. 73% of the universe is this mysterious dark energy. 23% is dark matter. I have not discussed it. 4% of this is us. We are a minuscule part of the universe. And on this very optimistic view, optimistic, which means we physicists has a lot more work to do for many years to understand what is happening. I would like to conclude. I hope I convince you that the cosmos is the last frontier of science. Every aspect of science happened there. We arrived at the age of precision astrophysics. We have new fundamental discoveries, but we have new mysteries, which should make us busy for a while. Thank you very much. And my apologies for the slide. Modesto, I thought we checked it. I thought it worked, but now here we are. It didn't work. Sorry.
No problem, Moshe. It happens. So we have time for one short questions. So the paper is open for discussion then.
Okay, I have a question. It's for me, it's very strange that the dark matter is not everywhere. It's localized in somewhere very far from Earth. Why is not isotropic the distribution of?
Okay, so what is happening? You're correct. It is everywhere, and what is happening? We are living in a very detailed balance of dark energy, which create anti-gravity, and gravity, which pulls us together. In our immediate vicinity, which means before the accelerated expansion of the universe, gravity is overcoming it. But somewhere 5 billion light years ago, the the anti-gravity became stronger, or not became stronger, it was always stronger, but overcome gravity. So it is everywhere. In the immediate vicinity, we are in the balance, which is they are roughly balanced, but 5 billion years ago, the anti-gravity, the dark energy overcame it. I hope I answered your question.
Well, thank you, Moshe. So in order to keep our agenda, so this is the closing session. Thank you to all of you, our distinguished speakers who be part of this session and help out to keep the level of this National Scientific Meeting. Thank you, Moshe. Muchas gracias a los colegas que nos acompañaron. Y el show de la ciencia continúa mañana. So the show, the science, is continuing tomorrow. So let's see tomorrow then. Have a good night.
Gracias. Hasta luego.
Thank you. Goodbye.
Gracias, Moshe.
Goodbye.
Thank you, Modesto.